All right, guys, Justin here from chemistrynotes.com, and this is video number 3 from section 13. Section 13 is called chemical equilibrium. Now, up until this point, we've only been working with homogeneous equilibria. Everybody's been a gas, right? Well, that's not always the case, of course, when you have chemical systems or reactions. We can have solids, we can have liquids, we can have gases, and we can have aqueous components. So today's a very short video just on heterogeneous equilibria. So some background first before we get started. It says heterogeneous equilibria. Thus far, we've only been discussing equilibrium situations in which all reactants and products have been in the gas phase. So we've had section 13 video number 1, and we've had section 13 video number 2 already. Everybody was in the gas phase. That's an example of homogeneous equilibria. So what I want to talk about now is when we have solids, liquids, gases, aqueous, all sorts of different types of reactants and products. What do we do? How do we write the equilibrium expression? Who can I include? Who can I not include? Who has a concentration? Who doesn't? Etc. So second bullet point there says many equilibria involve more than one phase. And that would be an example of heterogeneous equilibria. That's our topic for this short video. So let's get started. I want to do an example here at the bottom of page 1. Calcium carbonate, which is a solid, in equilibrium with calcium oxide plus carbon dioxide. Right? And this is balanced. Everybody's 1 to 1 to 1. Now, if we were to write our equilibrium expression the way we've learned so far, we would expect products over reactants. We'd expect CaO concentration times concentration of CO2 divided by the concentration of CaCO3. However, that's not what's observed. What we observe, or what the correct equilibrium expression is simply K, capital K, our equilibrium constant, equals CO2. And that's it. K equals concentration of CO2. So what's going on? Well, let me load page 2 here, and it says, I'll rewrite what our equilibrium expression is. It's K equals the concentration of CO2, and it says we've dropped out all of the liquids, which there weren't any, and solids. So the general rule is you don't include liquids and solids. You can't have a concentration of a liquid and a solid. They're already fully compressed. They're as concentrated as they're going to be. Gases and aqueous, those states, those can have different or varying concentrations. So those are the ones that we include. All right. So it says we've dropped out all of the liquid and solid reactants and products. Why? Well, because the concentrations of pure substances, such as liquids and solids, cannot change, and that's the concentration cannot change. So that's how we can just drop it out. Now, what does it say about equilibrium expressions? It says equilibrium expressions only include aqueous and gaseous components, meaning reactants or products. All right? So a solid is pure, it's compressed. A liquid is pure, it's compressed. They're not going to have any varying concentrations, okay? All right, 3 stars there. Equilibrium expressions only include aqueous and gaseous reactants and products, all right? All right, well, let's do some examples. Write equilibrium expressions for K and also Kp. Remember, my K is kind of like a Kc. So, P4 plus 5O2 yields P4O10. So if we go through, we only have one gas, and it's in the reactant side. So we have a placeholder 1 at the top. K equals 1 over the concentration of O2 to the 5th power. And then we follow suit with Kp is equal to 1 over the partial pressure of O2 to the 5th power. All right, B, NH4NO3 solid yields N2O gas plus 2H2O gas. So my K is going to be products, and we're not going to include the reactants, so there is no denominator here because that would be a solid. So we have K equals N2O concentration times the concentration of H2O squared, or Kp equals the partial pressure of N2O times the partial pressure of H2O squared. The reason why I don't use brackets for partial pressures, instead I use parentheses, is because brackets in chemistry represents concentration. Okay. C, NH4NO3, aqueous, yields N2O gas plus 2H2O liquid. Same equation, but different states of matter. K equals the concentration of N2O, all over the concentration of NH4NO3. All right, and the Kp expression I've dropped that one in this particular example. All right, so double line and a star. Next video is telling us is going to be on what? Applications of the equilibrium constant. This is when we get into something called the ICE method, initial change equilibrium. So the ICE method is probably the most tested part of chemical equilibrium. There's a certain way to do it, and you can do it the same way every time. And so that's what our next videos are going to be about. So stick around for that.